Here's an application of least squares, fitting a line to data. So here's some completely made-up data that gives average brain mass as a function of age after age 45. Here's the data plotted. Now, let f of x be the function that predicts average brain mass for a given number of years x. We might have the hypothesis that brain mass decreases linearly, at least after age 45. That is, that f of x has the form f of x equals m times x plus b for some numbers m and b. And our goal is to figure out what those numbers are. Which numbers m and b should we choose in order that this function best match our data? And what do we mean by best match? Our goal will be to minimize the sum of squares of prediction errors. So here's a line. These are the points. We're trying to find the line that best fits these points. The prediction error on a particular observation is the absolute value of the difference between the prediction and the actual value. And the sum of squares of prediction errors is just the sum of squares of those differences. Here we're zooming in on the graph. Now, you might think that the way to measure error corresponding to an individual data point is to compute the distance of that data point from the line. Okay. In this case, the line is not exactly vertical. That's the wrong way to do it, in fact. Keep in mind that the units of the horizontal direction are years, and the units of the vertical direction are pounds. So in what units would this distance be? It just doesn't make sense in the context of this problem. Instead, you measure just the vertical distance. That's the distance between the predicted value and the actual value. To find the line that best fits the data, we used our algorithm for least squares. We formulate the problem as this least squares problem, where we have a matrix A whose first column consists of the first coordinates x1, x2, x3, x4, x5, and whose second column just consists of ones. The unknowns are m and b, and the right-hand side vector consists of y1, y2, y3, y4, y5. What does this have to do with fitting a line to data? Note that the dot product of row I of the matrix A with the vector b is m times xi plus b, which is the prediction of the line model for that particular datum. So the vector of predictions is this matrix A times the vector mb. It's this product. The vector of differences between predictions and observed values, therefore, is A times mb minus the observed values. And the sum of squares of differences, that is, the measure of the error of this line, is just the squared norm of this vector. So the method of least squares will find us the vector mb such that m times x plus b is the best line, the line that best fits this data. There were a bunch of products, and we wanted to figure out how many of each product a factory was making by measuring the resources that they were consuming. We had a table that told us for each unit of each product how much of each of these resources was needed. And we found out how much of each product was made by solving the vector matrix equation u times m equals b, where b is the vector giving the amount of each resource used. So here's the vector b. We use solve, and what we end up with is this vector u, which gives the amount of each product being used. Okay, so that works great, except that it's really an unrealistic scenario. When you measure something, like the amount of a resource being used, you're probably going to get not the exact value, but an approximate value. So instead of the vector b representing the true amounts of each resource being consumed, what we'll probably get is a vector, we'll call it b tilde, which is an approximation to those, where each number here is an approximation to the true amount. Now, but solving with b tilde instead of b gives us this, which is a really bad answer, right? For example, here the number of shooters that were manufactured was 75, but our solver came up with 594.34. So it seems like we can't get accurate outputs when we have only approximate inputs. Slight changes in the input data lead to big changes in the output. So the output data is not accurate and possibly useless to us. So how can we improve the accuracy of the output without getting more accurate measurements of the resources, without having more accurate inputs? And the answer is we take more measurements. So in this problem, we have to measure some other resource. This isn't really a resource, but let's say we could measure the amount of wastewater produced by this factory. So now we get a slightly bigger table with one more column. The new column tells us for each product how much wastewater is produced per item manufactured. Now our measurement has one more number, the total amount of wastewater that's produced by the factory. Now if we look at the equation, u times m equals b tilde, it's more constrained. There's an additional equation. As a consequence, in fact, since we're using this approximate data, this equation has no solutions. It's too constrained. So what do? Well, we find the least squares solution. The least squares solution is this, which is a pretty good approximation of the real answer. So we saw that we can get better output accuracy without improving the input accuracy by adding more equations and by using least squares.
Here we want to estimate the current draw for each hardware component in our sensor node. We define the domain D to consist of the names of the hardware components, and our goal is to compute a D vector U that for each hardware component gives the current drawn by that component. We did this by running 4 test periods. We know the total milliampere seconds for the sensor node in each of these test periods, which we write in this vector B. And in each test period, we know how long each component was running. We specify those durations in vectors, duration 1 through duration 4. Now we form a matrix A, whose rows are the duration vectors, and we solve the equation AX equals B. If the measurements we put into the vector B are exactly accurate, when we solve AX equals B, we get back the true current draw for each of the components. However, in a more realistic scenario, our measurements are only approximate. Let's call the resulting vector tilde B. When we solve the equation AX equals tilde B, we get only rough approximations to the true current draw per component. How can we get more accurate results without making more accurate measurements? We need to collect more data. We add some test periods. Here we've added 4 test periods and collected the additional data. The measurements are still only approximate. Now when we form the matrix vector equation AX equals tilde B, we find it has no solution. Because of the approximation, the constraints conflict with each other. However, we can find the least squares solution, which gives us more accurate estimates of the current draw for each hardware component. Once again, collecting more data and using least squares gives us more accurate outputs without having to improve the accuracy of our inputs.
Finally, let's recall the breast cancer lab that we did. The problem was this. We had a bunch of vectors specifying features of different specimens and values specifying +1 or -1 according to whether the specimen was malignant or benign. Informally, the goal was to find a vector W that helps you predict whether a specimen is malignant or benign from the feature vector. And the way it would do that is the sign of the dot product of the ith feature vector, AI, with this vector W was supposed to predict the sign of BI, which is whether the specimen is malignant or benign. Formally, our goal was to find the vector W that minimizes this loss function, minimizes the sum of squares of the errors. And the approach we used in the lab was gradient descent. Now, I don't know about you. For me, that took a few minutes, and it actually came up with an error rate of maybe 7–8%. Can we do better with our least squares algorithm? So remember, this is the goal, to find a vector W that minimizes this sum of squares. Well, we can rewrite that sum of squares as the squared norm of a vector B minus A times x. This is just the least squares problem. So we can go ahead and use the algorithm based on QR factorization. It takes a fraction of a second, and it gets a better solution, a solution with smaller error. Now, this is just the very beginning of machine learning. You can use a lot more sophisticated methods to get even better solutions, such as using a different inner product, not the dot product, an inner product that reflects the variance of the various features. You can use linear programming to optimize a slightly different cost function, a slightly different loss function. You can even use convex programming to minimize some more sophisticated loss functions. All of this is beyond the scope of this course. But now you have the ingredients, so you can go learn it.